Hello, and welcome everyone to the next event in our webinar series. It's a presentation by Dr. Ryan Priore, Technology Manager at Thorlabs Spectral Works. My name is Malachi Schultz, and I will be moderating today's talk. Ryan is a spectroscopist by training and was spent most of his career designing spectroscopy and hyperspectral imaging tools. Thorlabs acquired his company, Certimo, which he was a co-founder in 2019. Throughout this presentation, we encourage you to submit any questions using the Q&A feature located below the media player. At the end of the presentation, Ryan and I will address these as much as we can at the conclusion of the talk. And we'll also find some additional resources and a short set of questions beneath the presentation slides. We invite you to engage with these materials as the session progresses. When you have time, your responses will provide some valuable insight. Thank you, and now I'd like to hand the talk off to Ryan.
Thank you very much, Malachi. I appreciate it. So welcome, everybody. So today, there's a lot of ground to cover and brief agenda here, so you know what's coming up. We're going to start with some objectives and then focus on some background, specifically the spectroscopy, imaging technologies, and leading up to exactly what is spectral imaging. I'm going to tell you a little bit about Thorlabs' new multispectral imager, the HSC23V, and then we'll end with some spectral imaging applications, and then blend in some questions and answers. So the objectives today, my goal by the end of this presentation is to give you a better understanding of the principles of spectroscopy, imaging, and spectral imaging. We're going to compare and contrast RGB, multispectral, hyperspectral approaches to accomplish this thing called spectral imaging. We're going to talk about some best practices for data processing, data collection workflows that are employed for spectral imaging. And then we'll talk about the HSC23V and really why we're so excited about this introduction into the catalog. And then finally, to close, we'll share with some spectral imaging applications. So I want to hit a little bit on the motivation for both this topic of spectral imaging as well as why Thorlabs is introducing a multispectral imager into the catalog, and maybe I should say future multispectral imaging systems to the catalog. Over the, my career and others, I've built a lot of multi-hyperspectral imaging systems, and there was really something missing in that space. And we sought out to develop something that was simple to use, it was flexible for the end user, but something also that was economical and able to bring you value beyond the traditional machine vision, RGB, red, green, blue color cameras that we're used to. We want to enable our customers to be able to configure the type of system that they needed specifically for their application. As I'll start here, as we begin, the visible and near IR spectral range is really just the beginning. We're excited to tell you more about that in time. So let's cover some background, and we'll talk about spectroscopy, imaging, and spectral imaging in that order. What you see on the screen already is getting to the type of data that one can acquire with spectral imaging. And with further ado, let's start talking about spectroscopy. So this image grabbed from NASA and is a very good example of discussing where we're going to start today, which is the electromagnetic spectrum. This is light, this is waves, this is the energy around us that we're interacting with right now as those radio waves, television waves are passing through us to the type of colors that you see emanating from your screen. And although light, which is both a particle and a wave, can span this very large literal spectrum, today we're going to focus predominantly on the light that is in the visible and the near IR portion of the spectrum, or light that overlaps with what is detectable with a silicon-based detector and camera. So that being said, the ultraviolet, infrared, microwaves, these may be familiar types of light-based or electromagnetic spectral ranges that you have heard previously. Now, spectroscopy is the study of that interaction between light and matter. Across that electromagnetic spectrum, how does that light interact with a material? And most often as a spectroscopist, I'm trying to understand something about that material. What's the concentration? What classification would I put this material that I'm analyzing? It's able to give us this material composition, structure, and as I mentioned, things like concentration or class. We can perform this across multiple spectral ranges, and we'll break that down as to the advantages as we talk about things like absorbance or fluorescence spectroscopy. But my research advisor, Mickey Myrick, once described, spectroscopy as elegant, and I think that's very true. It's a non-contact, non-destructive material analysis. You simply send light, and you see what happens as it interacts with that material, and is very popular to be used for quality inspection process monitoring. The type of data you generate is called a spectrum, and it is a plot of x-axis being wavelength, energy, color, and that type of light material interaction that you're seeking. This example one here is an absorbance-based transmission measurement. We'll talk more about that in a little bit. In the tooling that a spectroscopist uses is a spectrometer. And Thorlabs sells a whole host of spectrometers. This one I'm showing you here, the CCT10. This is a fiber optically coupled spectrometer that you can attach to your computer with USB 3. So there are a multitude of ways that light and matter can interact, and this is really just a couple examples to help support the additional content we're going to talk about today. But if you imagine that the red arrows, that is the light interacting or approaching that material, it can reflect, so the light bounces off of that material. It can refract when I have this change of refractive index at a particular interface. That angle that the light transmits through that material will change. But when it comes out the other side, we'll call that the transmission. And we can measure the reflection, the transmission, and we can even go as far as understand something called absorbance, or how much of that light was absorbed by that material. It's also quite possible that as that material takes on that light, we excite it into a higher electronic or vibrational state. And in the example of a higher electronic state, it can give off that light in the form of fluorescence. And these are the types of technologies used in for neuroscience or any of the medical device or fluorescence chromophore type analysis in order to tag and understand the material that you're looking to measure. And although we will not cover this specifically today, there's another type of interaction that can occur, which is simply scattering. Rayleigh scattering, as that light hits a surface, it will scatter from the incident source based on the same wavelength that originated. But there is such a technology called Raman spectroscopy, in which 1 out of a million or so photons will scatter at a different wavelength based on the electron cloud of that particular molecule. So today, specifically, reflection, refraction, transmission, absorbance, fluorescence. But there are both spectral imaging, hyperspectral imaging tools being used on the Raman side, and we will not cover that today. So let's talk about absorbance spectroscopy. So on the left-hand side, I have one of our cuvettes that we sell in the catalog, and I'm showing you some arrows representing different wavelengths of color. And below that, I have the calculation for absorbance, which is equal to the negative log base 10 of the transmission that we can measure on the other side of that cuvette. Typically, you'll remove that cuvette from your beam path. You'll collect a reference measurement. You will place that cuvette back into the beam path, and then collect your sample measurement. It can also be performed by keeping a cuvette with an aqueous or your solvent and then simply introducing your material. The middle, I have some diagrams here, S0, S1 representing electronic excitations or transitions within a molecule. And then you'll see V0, 3, V4, and these are just a couple of the type of vibrational transitions that you can excite within a molecule. So in order to understand absorbance spectroscopy, let's start with the infrared light. This is the lowest of the energy range of the light that we are going to be discussing today. And what actually occurs is as that light is absorbed by that molecule, when there's a change in partial charge across that molecule or that bond, we have an induced dipole moment, and the light that is absorbed actually excites that molecule into a higher vibrational state. And as we sweep through and look at the wavelength that I have, the spectral plot that I have below, we can identify those types of transitions. So With that, we can actually probe specific molecular bonds that we're interested in for that particular material of interest. Now, if we move to a higher energy range, the shortwave infrared, we can now have combination bands or higher order absorptions that are occurring with that fundamental infrared-based measurement. Now, we're also moving across the spectral domain closer to the visible, but this is still a region outside where our eyes are able to detect it. But with sufficient detectors like InGaAs, just to give a particular example, we can now still identify these types of transitions and vibrational bonds that make up the particular material of interest. SWIR is a fantastic spectral range that can be used for identifying the concentration or classification of a material. But now we transition into the visible and the UV. We're not only migrating from a vibrational excitation or a base transition level, but we're now moving into an electronic state. We've now excited that molecule to which that electron has now absorbed that energy and moved into an electronic transition. And as we move from the infrared into the visible to the UV, you'll see that those features become broader and broader. The point at which they can begin their excitation or end becomes, there's many more opportunities for that transition. So the less specificity that we have in identifying the original bond, but can still be used as a methodology for identifying material. Absorbance is a fantastic technology also because using something called Beer's law, we can directly relate the absorbance of a material with concentration directly. Another type of technology, as I mentioned, we're going to discuss is fluorescence spectroscopy. As we excite that particular material, we send that light in, it is absorbed. It could be a laser-based, it could be a broadband light source. And at this point, as we have that excitation, we have a relaxation which is occurring, similar to the absorbance type spectroscopy, but we can have a re-emission of another photon at a longer wavelength. And that is the fluorescent light that we're able to detect. These are really the basis of designs of things like chromophores, or if you've ever put a highlighter in water and hit it with a black light, you see this type of re-emission of that photon. Now, an example spectroscopy experiment consists of a light source, some optics to steer that light to the sample, sample handling, which I will argue is probably 90% of the challenge, getting your sample to the beam probe or how to make that measurement. And then with additional optics, we send that on to our spectrometer. And as we talk about spectral imaging, you'll find that this is very similar, except we're just going to replace some of our components here with something that can produce an image. But in order to collect high quality spectroscopy measurements, we're really trying to optimize that photon signal. While, on the other hand, we're trying to minimize any of the noise sources in our measurement from optical, detector, electronic, or even the experimental noise through perhaps a lack of a design of experiment for the type of measurement that we're attempting to make. And this propagates throughout the measurement chain. So specifically, let's hit on 6 different points of what one needs to focus on in order to collect high quality spectroscopy data, which will also translate to spectral imaging as we discuss later. And the first is simply your light source. We want to ensure that if we're going to be probing and measuring features, that we also have a light source that aligns with that particular spectral region. Now that may sound, a little bit, trivial. Well, why would you have to say that? But if we look at the lamp profile of an emission, say for one of our SLS 201L, we can see where the actual power is being emitted. And we would want to select our light source that we're overlapping with the highest amount of photons that we can throw at that sample in order to make that measurement. We want to minimize the noise, the color shift of that lamp while we're using it. And in some instances, we may choose to chop or modulate that source to overcome any background illumination that we may see, or the ability to lock into a particular frequency in the measurement related to the electronics of the system that we're designing. We also want to collect as much of that light as possible, and this comes down to our optics. So we want to select high numerical aperture optics. If this was a microscope, we would want to look at perhaps a high numerical aperture objective, and that's really, in the end, just the amount of light that we're thinking about an angle of collection. we want to maximize that collection that we possibly can into our system. Obviously with trade-offs such as the depth of field and some other details that are beyond the scope of this discussion today. But it allows us to optimize, at that point, the alignment. We want to minimize any loss or stray light, and using high transmission reflection optics and coatings where possible. This may be gold in the shortwave infrared. This may be protected silver mirrors in the visible, or even, another product that we produce is textured windows that allow maximum transmission of a UV-VIS silica-based substrate in order to minimize the losses of light that you typically would have at glass air interfaces. We should be thinking about the resolution and the bandwidth. Spectral features, as we discussed, from the infrared into the visible, they become broader and broader. So the selection of your slit, or what is constraining your wavelength discrimination of your tool, that it's aligned with the type of features that you're trying to analyze. So we may want high resolution, but with high resolution, narrow slit, we throw away a lot of that incident radiation. And perhaps we can match the slit, the grating, and some other components of our spectrometer in order to optimize the measurement for the configuration and sample that we're measuring. When thinking about detectors, you want to look for the highest quantum efficiency detectors with the lowest dark current and lowest readout noise possible. In some instances, this involves cooling the detector. And ultimately, we want to utilize a signal that's been optimized based on photons hitting our detector. Secondly, we can adjust the gain at that point in order to optimize the dynamic range that we have available to us. And once again, I'm showing some example detector efficiency curves that you can find on our website to find the appropriate detector for that type of spectroscopy measurement. Another key consideration is measurement time. If you have, if time, it's a slower type process for the event that you're measuring, well, you can increase the integration time in order to optimize your signal to noise ratio. Now, with that, there are some diminishing returns as we increase that time. We actually, assuming we're in a photon counting regime or a photon flux mode, that this enhancement that we're going to see in the signal to noise ratio is actually going to increase as a square root of that time, or perhaps averages. Averaging, as I just mentioned, is another way that you can repeat measurements and improve your signal to noise ratio. And then the last one, which is typically overlooked, is the actual experimental design itself. That if we are looking to make a specific measurement, have we optimized those variables that are most important for the measurement at hand? Are we sufficiently varying both the background, the matrix, or things that can lead to noise, anything in our final signal that we really don't want to measure, while optimizing the analyte or the thing that we are trying to detect? In many instances, there may be multiple analytes. And before we go use this tool in a routine measurement, there's a calibration, a set of data that we're going to want to collect that ensures that we're able to discriminate that key component from that background matrix or the noise. So as we start to think about processing data, one way that we can think about a spectrum is that we can view it as a vector, or simply a position in space that we are pointing to. Now, spectra may have hundreds of wavelengths that we're utilizing in that measurement, which is part of its value. But in this simple example, let's reduce this down to 3 wavelengths that I've selected, one at 500, 650, and 700. And if I take the intensity of those 3 wavelengths, I can plot those in 3-dimensional space. And what I have is a 3-dimensional vector. Now, we can envision and think about things in 3 dimensions, but that 250 member spectrum could be viewed as a 250 dimension vector. And with that, we can do vector math. Now, I'm not going to take you back to Calc 3, but giving you some examples on the far right-hand side, if I have 2 vectors A and B, I can add those together I can even subtract those two vectors from one another. And even on the bottom, the basis for many of the advanced calibration or multivariate statistical analyses or machine vision, machine learning, or even buzzwords like AI fundamentally come down with a computation that is the dot product, where I can take two vectors, I can multiply them by one another. And a simple way to think about this is the projection of one of those vectors onto the other. So in my example on the bottom, with two vectors, B and A, if I'm looking at the dot product, we can envision this typically as, say, the sun casting a shadow with a sundial. What is the projection of that one vector onto the other? And in this example below, I show that we can calculate the magnitude of that, of B on top of A. Now, if these vectors are orthogonal to one another, that projection is 0. Okay, let's move on. So calibration, I want to take this spectroscopy measurement and signal, and I want to do something with it. So in very simple situations in which, perhaps you have a correlated system to species in which I have varying concentrations. Well, that varying concentration is really what I want to be able to identify in future measurements. And in these simple mixtures, if I select any two wavelengths that don't occur at the isobasic point, where I see the crossing or transition of those mixtures together, I can construct a rather trivial calibration. I'm showing you 3 dimensions in that plot, but this could really be drawn back to 2 for the simple example I have. And once again, each of those points we can think of as a vector. But things get complicated, and they get complicated whenever we add some type of interfering species, something in the background, the matrix, a noise source, most often uncorrelated and not planned for in that particular measurement. So now in this uncorrelated noise source, which we have added to our mixture, that simple linear calibration that we once drew is no longer so simple or linear for that matter. But if we think about these once again as vectors, points in space, there is actually a direction that exists, a direction in which I can rotate my data set and identify a unique position in which I maintain and regain that linear relationship. What we've done here, if we think about the vectors once again, is that I found a position in that cube's dimension in which I am aligned with my signal, which would be a vector in the plane of your screen that you're looking at right now, while that interfering component is actually a vector pointing out at you at the screen. And since these are now orthogonal, I can see that this is minimizing its impact on the measured signal that we have. So now as we transition from spectroscopy to imaging, we're relatively familiar with imaging. We all most likely have used a camera. We've most likely used a color camera that has the discrete red, green, blue channels. Now, cameras from our cell phone to even digital SLR cameras to machine vision cameras that are used in industry, ultimately the goal here is to capture that spatial distribution of light in order to give a visual representation of an object. Now I'm showing a cartoonish image on the far right, but we have an X dimension, a Y dimension, and the individual elements or the pixels that make up that image. One could argue that simply 2 pixels make up an image. There's a spatial distribution of something that I'm trying to visually represent as an object. Now, it answers questions such as where is the thing? We preserve the spatial relationship, size, shape. And conventionally, these are measured with broadband intensity cameras, mono, meaning that sensor is sensitive to all of those wavelengths simultaneously. If this was a silicon camera, this could be something from 400 to 1100 or 1000 CMOS type cameras, sensitive at one time. If we're talking about an InGaAs, this may be 1 micron to 1.7 microns. All wavelengths generate signal at the same time. Now, when we talk about color or RGB, cameras. We won't go into the details of an RGB camera, but each of those pixels themselves have individual filters that can limit the color that is measured from red, green, and blue in a repetitive pattern or kernel across that sensor array. And from that, we can recombine what those specific colors were. Now, when we look at the use of cameras in industry or other disciplines within the scientific community, these are cameras that have a much higher dynamic range. We are talking, 16-bit type of measurements. The cooling, the noise floor, all of these details are things that we look at. But ultimately used for supporting and understanding defects, geometry, edges, texture, and uniformity in a particular measurement. Now, not all imaging techniques are equal. And this slide is really to show you that we talk about imaging, we can produce images with multiple types of technologies. The ones in red are really the ones that we'll focus on today, but you may be familiar with millimeter wave measurements if you ever walk through the screening tool at an airport, or you've sent samples off for SEM imaging, generates an image that gives you very small features that you can resolve, but not necessarily telling you anything about the chemistry or the molecular specificity, as you see on the left-hand side of this plot. Or even an MRI from a medical imaging in which we have this ancillary information of the chemistry that's going on based on how we can observe attached components like a hydrogen in that particular sample of the tissue that's being measured. And as we work our way up to the top, we can gain higher and higher specificity so that the image that we're collecting is not necessarily just based on color, but it's based on the chemical content that we are trying to identify. Now, the basis of this presentation is on spectral imaging, and we could probably take each of these components and talk about them in much greater detail. For simplicity, we're going to treat the camera as a detector, and things like quantum efficiency, the sensitivity, noise readout, and so on and so forth. I would welcome you to check out a host of informational content also available on our website and a previous webinar where we've discussed in much greater detail the types of cameras that Thorlabs both manufactures and sells in our catalog. And similar to how we talked about spectroscopy, we can process this data in a variety of ways. We talked about spectra as being, multiple measurements as a function of color or energy. But the image itself is this two-dimensional structure. And if you've ever used image processing tools, anywhere from web tools to Adobe Photoshop or even the open source tool GIMP, you can play with a bunch of these types of features. We can extract something based on a color range. We can convert color images into grayscale, which this could be a specific RGB intensity measured on the camera, or this can simply be a composite of those individual colors. We're able to use kernel filtering. One that's most familiar would be a Gaussian blur. And the way kernel filters operate is we have a subset of pixels as a window, 3 by 3, 5 by 5, which each represent a coefficient. And those neighboring pixels are multiplied by that coefficient, and the central pixel is replaced with that final value. And this is the basis for how we can blur, median filter, or even detect edges of objects within an image. We can threshold based on intensity, and this usually isolates a particular feature that we're interested in identifying. We can even invert that. Now that we have an image of just ones and zeros, we can flip that into zeros and ones. And the purpose of this would be perhaps for additional downstream processing that we're interested in. For example, we can multiply that by a image of simply one value and result with some final output based on this image map. Certainly not exhaustive, but to give you a sense of there are spectral processing that can be performed as well as imaging. So exactly what is spectral imaging? So now we combine these two components in order to generate a fully resolved data set that has both spectral and spatial information. Each pixel within this data set now represents a fully resolved spectrum, something that helps us identify now specifically what is the what. Is this a compound of interest that I'm searching for? Can I take a signature of something known already in a database and identify its spatial location within an image? Now, as I mentioned, with monochrome cameras, we can think about the intensity that's measured as simply being the broadband intensity that we're able to sense. And red, green, blue, or RGB cameras have dedicated pixels related to the color of interest and only allow the capture of that particular color that we see at any given time. So we increase the specificity, but really just to color. If we go one step further, we now have a multispectral measurement in which we can fully resolve to a degree based on discrete bands that we identify that may be aligned with the analyte of interest, all the way to a fully hyperspectral, in which the assumption is this is a continuous set of spectral measurements that are made that give us a higher degree of specificity within the sample. Now, I thought this started off as a good idea to introduce you to the Spectral Data Cube, and as I showed you the world's worst DMV photo, we can see that with our HSC 23B and 12 measurement channels, we can extract some additional information that may not be obvious from an RGB or a color-based measurement. Once again, we have a stack of images that have now both spatial and spectral information. We can recreate a pseudo RGB image by simply extracting 3 wavelengths from the data set and combining them back to create a composite image. But as I look at 3 particular regions within this image, I can learn something new that may not be there simply from the RGB. Specifically, as I look at the forehead ROI that's drawn here, we notice that as we get closer to the ultraviolet or the 400, the deep purple portion of the spectrum, there is a much larger absorbance that we observe here. And as we get to the UV, this is the basis for why sunscreen would be an important thing to measure because of the high absorption that we see as we get closer to the UV, specifically with skin. And the background has a signature associated with the wood panel. But most interesting is the ROI selected on my black t-shirt. As we get past 750 nanometers, that dye in that particular material is not necessarily black anymore. It actually looks like I'm wearing a white t-shirt as I get between 800 and 950 nanometers. So there's more to the eye as we transition away from RGB into multispectral or hyperspectral data sets in those spectral ranges outside of traditional red, green, blue channels. Multiple ways to create this spectral image. As we just alluded to in the multispectral, we're collecting specific wavelength bands, colors as a function of time. But we can look at point mapping, which is simply sending discrete points of interrogation to a spectrometer in which we collect a full spectrum as a function of spatial location. And by raster or serpentine scanning, we can create that data cube. If we're familiar with a Xerox copy machine, when you place your paper down and we see this line sweeping across the document, in a very similar fashion, we can use line scan technology in order to generate that hypercube, where we have a full line or image that is collected for a full spectral measurement, and we sweep that as a function of time to complete the cube. The basis of today's discussion is on the wide field in which we can tune a set of filters or electronically with a liquid crystal tunable filter or acousto-optical tunable filter and generate the specific color, wavelength, or energy value as a function of time. And last but not least, although we won't talk about it in much detail today, is the snapshot imaging approach in which we can collect that entire data set, spatial and spectral, with some additional post-processing in one shot. So let's talk about some historical spectral imaging challenges. And a lot of this comes down to things like the complexity. When we think about RGB cameras or even mono and machine vision, we have 3 wavelength channels, color, or just a simple intensity. And when you add more wavelength channels, that processing becomes more important. And this has been hesitation at times because you have additional knowledge that's required from both the end users and those who are interpreting the data. So it tends to be viewed as having a steep learning curve to limit the adoption. Perhaps it's flexibility. In order to utilize these types of systems, you're either buying fixed band configurations for the application, which limits your ability to use that tool for something different, and being able to change those filters or wavelengths of interest that you may not have that where you sacrifice or trade price for flexibility. And when you add software, not necessarily, at least on the industrial side, to have a open platform in which we can use tools across different modalities together. And cost. So hyperspectral imaging systems, it's not uncommon to see things in the upper 100, 200 or higher thousands of dollars in order to identify a system and use that in your lab. But even multispectral systems, depending on that type of configuration and spectral range, can get you anywhere on high-end systems approaching $50K to $100K. So this limits the opportunity for folks that may be budget constrained or startups or exploratory industrial users to enter into this space. And once again, data processing could be its own webinar that we could talk about. But I think to give you the high-level understanding of what one can do is post-data acquisition, there's a series of pre-processing, multivariate statistical analysis to identify the features that are of most interest for that specific application, to be able to generate a final report for decision-making. And there's no amount of processing that can be performed to get over bad data. So as we think about the collection of the type of data, coming back to my comments earlier about high quality spectroscopy data, it directly translates to this type of measurement as well. Pre-processing, in my opinion, is not optional. This is the difference between a simple camera and a measurement instrument or tool. Things that we typically do are looking for dark correction, subtraction from that particular sample. White referencing, flat filtering, normalization of the intensity profile of our scene, as well as accommodating any geometric corrections or registering one wavelength band to another if we see shifting as a part of that collection. Now, one way to think about this, if we look at what happens whenever we have a raw image versus a reference image that we have, this is related earlier talking about an absorbance measurement. We're going to ratiometrically correct that measurement against a known reference in order to give us something that will not just simply scale with our intensity level, that we can come back to and using transmission reflection, correlate this via absorbance with the property of interest. There's a whole host of additional spectral imaging data processing that could be performed from averaging both in the spectral domain as well as the spatial domain. This type of smoothing, things like Sophisticated or simple boxcar are tools that would be used in the spectral domain. As we mentioned, some of the kernel filtering options traditionally in image processing also applies here for spectral imaging. One that I want to point out, or at least draw attention to, is normalization. And this is in which we take what looks like an image as I extract a single frame. And although there may be the same chemical consistency across that image, the texture or physical properties of that sample may make it appear, based on that image contrast, that they're different. And things like normalization are performed in the spectral domain, in which we can set the area under that curve equal to 1, which is what you see in the example of a 1 norm, or even set that to unit length of 1, which would be the 2 norm or vector normalization. And you can see in the processed image extracted from a single frame, the texture is reduced, and you're left with that final type of information that we're looking for that spectroscopy-related contrast and not simply texture. So let me tell you about the HSC23V. Multispectral imaging is a sweet spot, and a lot of this really comes down to having the spatial resolution, simplicity, and specificity in order to tailor it for an application that you have. It extends us beyond what's capable with traditional red, green, blue, or RGB. And it can still be incorporated to the same type of level as RGB for high throughput inspection without that cost and compute overhead that comes with traditional hyperspectral imaging. I have some tech specs here for that system, and you can find much more information on our website. But this is a C-mount based system. We're sensitive across 400 to 1,000 nanometers. Pixel size is 5.86 microns. And with this particular system, it operates off 12-volt power and uses USB 3. Not only can you use a C-mount lens, but it works with our cage system, both 30 millimeter and 60 millimeter cage components. And there are also multiple holes, quarter 20 tapped on both the bottom and the side, which you can see 2 of those here in this particular image, for mounting either to a tripod or to post onto an optical table. The HSC features 12 slots in which filters can be installed that can be tailored for your measurement system. We sell these as kits, which we'll talk about in the next slide, with varying full width half max and wavelength positions. And this allows you to mix and match and customize a particular measurement system and change as you desire for the type of application at hand. This gives you that flexibility we mentioned in the beginning, as well as being an economical approach to solving that application problem that you have. You can buy extra wheels, as we have available on the website, and populate them with filters that you desire in the kits that we offer. And each of the kits themselves, we show the transmission values of those particular filters on our website. This example, we cover both the 400 out to 950 nanometers, 2 different options, one with 40 nanometer full width half max, and another set in which it gives you a 10 nanometer full width half max. We also sell kits that focus on the different regions of the camera, although it's a silicon-based detector, the traditional visible portion of the spectrum that we're used to seeing with our eyes, from 380 to 710 nanometers with a 10 nanometer full width half max, or shifting to the near IR sensitive range of the camera from 650 to 980. And if we don't have the wavelength that you need, we also do customs. We also do custom solutions if this needs to be incorporated into a larger type of assembly or system that you have. Reach out to us and we can give you more information. The software runs on Windows 10 or 11, communicates over USB 3, and has been really configured right now for acquisition, in which the user can independently optimize the exposure or gain for those specific wavelengths of interest. You can output data sets today in the form of OME, TIFF, or TIFF format. Downstream processing in your host of tool or interest, from MATLAB to Python to your own custom application. And all of this, as a multispectral imaging system, you can enter in at sub 13,000. So the system itself, plus a lens of your choice also available in the catalog, plus a filter kit to get you started. We're going to end the talk today with a couple of spectral imaging applications that give you an initial taste of what you can do with the HSC23V. There are plenty more here. And as you see when we're at trade shows, you can see live demonstrations that we will show there, as well as systems that we have available that customers are asking for as loaners or testing today. One example, this was collected by our Thorlabs colleague, Thomas Schmidt, in which we took just a traditional bottle of Coca-Cola, and I have generated an RGB composite image once again by selecting the 450, 550, and 650 nanometer image into the lower right. But as we sweep through those specific wavelengths, we can see that after 750 nanometers, Coke is no longer dark. That dye that we're used to observing of that color of cola becomes almost transparent as we get out to the near infrared region of that spectrum until we start approaching where water will start to absorb. But this type of interest here is, how could you look for particulate analysis, or how could you identify anything else that may be within a traditionally opaque solution that could not be resolvable today with an RGB camera. But being able to select wavelengths in a flexible system outside of those spectral ranges enables you to pursue these types of applications. Another interesting application is looking at the transmission of light based on heat control window film. So a film that's applied to glass in order to optimize the efficiency of the HVAC inside of a building. It touts two things. First, to minimize the UV transmission to protect items from UV degradation inside, but as well as blocking those longer wavelength infrared wavelengths that may contribute to excess heat generation inside that facility. So what we're showing here is a halogen shop lamp that is mounted behind a window where the film has been installed in an oversaturated image from the HSC23V to produce a RGB composite image in which you see a fully saturated lamp, which you would observe if you saw that with your eye. And as we sweep through those wavelengths, we can see that it does start to appreciably drop out to 400 nanometers. But as we get to the near infrared portion of the spectral range, we can also see a dramatic decrease in signal. So the product is doing exactly what it says it's supposed to do. And even more interestingly is that if we were to take the 950 nanometer image of what you see on the left-hand side, you're actually seeing a very high reflection of what is happening behind where this measurement was made. You see a lamppost in the background and reflection off of the grass and ground behind it. So this is actually reflecting those wavelengths back out. Another area of interest for a tool like this is looking at vegetation indices. Now there's a variety of these types of values that are used in precision agriculture or in that particular field of study. Predominantly, it's to understand things like the vegetation density or overall crop health. One can look and tune for things like chlorophyll or even carotenoid content. And I have a handful of these values here. And as we look at wavelengths that we can configure for the HSC23V or wavelengths close to the intended values from that formula, we can generate these same types of maps that can be identified or utilized for understanding something about that particular plant. So in this example here, we have a cell phone camera image on the far right side, in which you see a variety of leaves that have been laid out across the field of view. And then after a collection of that data set with the HSC23V, using the formulas in the previous slide, and using a jet color scheme for each of these images instead of the monochrome 0 to 1 grayscale, we're able to show the type of information that would come from that type of calculation. So the the NDVI 705, this is giving you some sense of plant health. And the higher we are, closer to red is a good thing. Closer to the bottom in blue would be, less healthy. And the other two, the GNDVI and the GCI, related to chlorophyll content, and finally the BGI related more for carotenoid. Each of these can give a researcher a particular additional piece of information, while also being able to retune that system for a future application or completely different application that they desire. And as we bring this to a close, although I'm showing you how you can use it for plant health, I'm wondering if any of you identified the plastic leaves that were thrown in here as well. And actually, if we look at something for identifying chlorophyll, which is the GNDVI, the GCI, we actually see that it's relatively non-existent. So with that, I'd like to conclude by telling you that spectral imaging combines both spectroscopy and imaging. Hopefully you took a little bit away today on a background understanding of both of those modalities and technologies, and how you can use spectral imaging specifically with a multispectral imager such as the HSC23V in order to generate data that you're creating contrast in your data set, not on color alone, but based on the chemical or physical differences within that sample. Multispectral imaging, as I said previously, I consider that the sweet spot. It extends a conventional machine vision system from RGB by capturing a small set of application-specific spectral bands that you can tailor for your application, improving the spectroscopic selectivity for your application compared to traditional RGB. It still enables you to have the high throughput inspection or research that you're able to perform without the cost, compute, and complexity that comes with a full hyperspectral imaging system. And the Thorlabs HSC23V system features a 12-slot filter wheel, allowing customers to mix, match, or even request custom filters that can be used for their application needs. So with that, I'd like to thank you for your time. And Malachi and I would like to open it up for any additional questions.
Thank you, Ryan, for the informative presentation. We appreciate it. Yes, like Ryan mentioned, there's a few questions coming in already, but again, just invite you, feel free to submit your questions down at the bottom ribbon. Ryan, one of the first few questions that came in was asking about sort of a workshop, webinar, or potential demo systems we might have available if people wanted to get their hands on these systems and try it out.
Yeah, so that's a great question. I would invite you as you visit us at trade shows. If the HSC23V is there, we always have it coupled with a live demo. We do get many requests for demonstration systems, and we're very happy to accommodate that. We have limited systems that we can send out, but that is very much a possibility. I think more than anything, I would encourage you to reach out and start a dialogue and a conversation. You could reach us at tsw@thorlabs.com. And we can even talk through and better understand and give some additional feedback about that system itself. Or perhaps it's not the right system for you, and we can better align that. So I think the short answer to that is yes, we do have systems that are available. It's hard to guarantee how quickly we could turn those around because of the demand, but certainly we can offer that.
And I would also say, I'll put in a little plug here. We will be at SPIE Defense and Security next week, and we'll have a demo there. So if you happen to be traveling, and please stop by the booth, we'd be happy to walk you through the system and show you a little bit more. Another question was a little bit about looking through the filter wheel and how much blue shift is present across the image when used with a narrow band filter. Yeah,
so that's a great question. And, one's mileage will vary based on the optical configuration that you are using, the particular numerical aperture or f-stop that you're using on your lens. I think in broad brushstrokes, what I could really describe would be these are still thin film filters. We know that interference filters do have a blue shift as a function of angle. Based on the type of angular field of view that would be passing through that filter, at least for the types of combinations for the machine vision lenses that you would be working with, one can constrain that angular field of view to produce a negligible type of shift. Now, this gets blurred across the image and based on the center of the image to the edges. And these are, I appreciate the question. It is a limitation with any interference filter-based technology. But these are things that can be minimized with the type of practice and experimental configuration. I'm going to tie this to another question that I saw popped up here that's also related to not if I didn't want to use a C-mount lens and I wanted to attach it to a microscope and I wanted to use a tube lens or an additional rail type configuration. And I think based on your selection and your final optical configuration and the final numerical aperture that you're sending onto the camera, those can be at least identified in advance to ensure that you're working within a small angular field of view, plus or minus 5, plus or minus 15 degrees, say, through that interference filter.
Thanks, Ryan. Another question came in asking a little bit more detail on potential applications for maybe time-resolved measurements.
Yeah, so you have the ability to adjust your integration time from the millisecond regime out to 10 seconds per integration. there is a settle time that we impose from filter transition to filter transition, about 160 milliseconds to stabilize the filter in front of the camera. Based on an optimized selection of the number of wavelengths that one requires, we can play with that measurement time variable while also assuming that you are optimizing the illumination, the type of aperture stop on the camera itself, in order to minimize the integration time required because you have a lot of light and the specific wavelengths of interest. So not to sell what we don't have, there's active development right now on a software development kit that once released will give the user the ability to identify a specific application collection in their choice of source code. So if you only need 2 wavelengths, you can set up a measurement configuration in which you're rapidly flipping between 2 or 3 or more for that type of measurement. So it's a pretty broad, there's lots of details there that would be optimized for that measurement, but if you want to monitor a single wavelength, we're at camera readout speeds that you could get. I think it's 40 frames per second, I think, for this particular system. But as you introduce filter changes, that number would be a variable based on the measurement that you're intending to make.
Awesome. And then I think I saw a question came in, and I don't know if we had it there at the end, but about the price range for this system.
Sure. Yeah, that's a great question. So as you know, at Thorlabs, we publish all of our pricing on the website. So the base system itself is $9,000 US. And with that, we have a filter kit that you would need at a minimum. That filter kit, I believe, is $2,710, I think. I hope I'm right. I looked at that. But it's sub $3,000 for a filter kit. Now, as you mix and match those filters with different kits, we hope in time to offer more wavelengths of interest. But please follow up with any of your custom requests because we do a lot of custom work. With those 2 pieces alone, those are your base costs, $9,000 plus the filter kit. If you have your own lens, then you're off to the races. So that's really where it will scale right now, at least with that HSC23B. That's the base price for that, and plus the kits. Everything else is really can kind of vary based on your selection of the lens. The example I think I showed there, that sub 13K, which I think I can push that to the screen here. That is if you purchase those items that we have on the screen.
Awesome, thanks. And I know we're coming up close to time here. We want to be cognizant of people, so we'll just do one final question. I see
Sure.
Where there's a person who's operating some indoor growth chambers and exploring kind of automated solutions for monitoring plant growth stages and disease progression. Would this be a usable solution? I know we touched on a little bit on some of the plant testing that we've done.
So that's both fantastic question and an area that I think we are extremely interested in talking to users who are doing things like that. I think this does give you an opportunity for being able to automate measurements with a flexible configuration of which wavelengths. And then from a processing scheme, although we have not talked about that today in lots of detail, but be happy to talk at length about those types of processing strategies to help you extract the most useful information from those data sets. So yes, please reach out to us, tsw@thorlabs.com, and we can help you both with your application or alignment with the appropriate filter selection to enable you to pursue these types of very fascinating and exciting applications.
Awesome. Thank you. And with that, I think we're at time for today. Ryan, thank you so much for this presentation. And thank you, everyone, for joining us today. We truly appreciate the time and engagement. I hope you found today's session valuable and informative. There will be a recording of this session sent to your inbox, and it'll also be available at www.thorlabs.com/webinars. So you can find it there as well. If you guys have any additional questions, we ran out of time today and you'd still like to talk more, please don't hesitate to reach out. We'd be more than happy to talk about either your current specific needs or any customization to this product that you need. So again, thank you again, and we hope to see you at a future event.
Yeah, thank you. Bye-bye.